All right. Hi. Welcome back on this gloomy late October day. So, today we are almost done with lists. You guys aren't almost done with them because you're gonna continue to get to struggle with them for a few more homework problems, but today I'm gonna quickly review the linked list insertion algorithm, and then we're going to start talking about a new data structure, trees, which is gonna consume us for the next couple weeks. Not only because trees are an incredibly powerful and useful data structure, but because trees are where we're gonna open up a new programming technique, a new problem-solving technique that's called recursion. We're gonna practice that on trees for a while. I'll give you guys some experience with that. Recursion is, again, really I want you to think of this as a problem-solving technique. There are recursive programs, but really what we're gonna be doing is implementing recursive algorithms. It's a particular approach to solving problems that proceeds by first making the problem smaller and smaller, solving simple instances of the problem once we've made it small enough, and then combining the results together. So those are kind of the three characteristics of a recursive algorithm. All right, but let's start off by quickly looking through our linked list insertion algorithm since we went through this quickly, and then we'll do kind of a table-based comparison of linked lists and array lists and talk a little bit about the trade-offs between the two. Remember, these two implementations provide the same interface to a user. So if you are writing a program, you can use either a linked list or an array list using the same interface, and your program doesn't have to change at all. The performance of your program will change, because these two implementations have different trade-offs in terms of how the operations actually, the performance of the underlying operations. But let's first talk about how do we insert into a linked list. So, and this is something that, you guys should follow when you're working on the homework problem, about insertion, okay? So the first, problem here is that we need to find the right place in the list. So a linked list stores the structure internally. And so we need to walk the list using something similar to the reference following for loop that we looked at last time to get to the place where we have access to the reference that needs to change. Now that doesn't turn out to be the index of the new item. It turns out to be the item that's before the item that we want to insert. So we find the right spot. Then we're gonna essentially we're gonna change some references around. And again, this is tricky to get right. You're gonna make a few mistakes when you do the homework on this, but this is, again, great practice for things that you guys will see in 225 and 241 and other courses later on, and also just general working with data structures as a computer scientist. Right? When we look at trees, we're gonna do a lot of reference manipulation as well. So essentially, I need to kind of insert a new link into my chain. And the way I do that, remember the chain is made up of these references from one item to the next item. So I found it, if I want to stick an item in the list, I need to both make it some other item's next item, so I change its next reference, and then I need to make sure that the rest of the list follows after the new item that I'm inserting. So I need to make sure that the rest of the list becomes, the first item in the rest of the list becomes the next item of the list that I'm inserting. Okay? So these are the two steps right here, and then I'm done. That's all I need to do. All right, so let's look at this on our diagram again quickly. So let's say I want to insert value 7. I want to insert a new item with value 7 at index 1. So when I'm done, this item will be the next item of item 5, and its next item will be item 8. That's one way to think about it. So if I can get a new item 7 such that item 5 have a reference to item 7, and item 7 has a next reference to item 8, then I'm done. That's what I want, okay? So the first thing that we noted is that that actually requires walking the list not to item 8, which is where I'm gonna put the new item. That's the item that's currently at index 1. I need to change the preceding reference. So I actually need to walk the list to item 5, which is the item at index 0. This makes a little bit of sense, right? If I stick an item at the beginning of the list, then the reference that actually needs to change is the start, right? So essentially I'm walking the list to the element at index -1. Doesn't really make any sense, but that's my start reference. That's the start reference that my list implementation holds internally. In this case, I'm gonna walk the list till I get to item 5. Now I have access to the item I need to manipulate. Okay, so now there are two steps. I have my new item 7. The first thing I do is I set item 5, I need to make it the next item after item 5. So I just did that here. And then I need to make sure that the rest of the list, so item 8, is the next item after item 7. Now, if you're not careful about how you perform these two steps, you can get stuck, because you might get to this point and think, oh, things are going really well, but I don't have a reference to the rest of the list anymore. All right, so that's where this becomes a little bit tricky. This is not hard to do. I mean, this is one of those, you know, small 2 or 3 line pieces of code that's just, subtle to get right the first time. Once you do it a few times, it'll make a lot more sense, right? So make sure that you keep a reference around to item 8, because you're gonna need it here to make sure that I relink the rest of the list on after the new item that I'm inserting. Any questions about this before? I know this is very abstract, that's kind of the point. It's, you know, you guys have been, a common, you know, concern I hear about this class is, oh, I have a hard time translating my ideas into code, and that's like, yeah, you know, that happens. I have a hard time translating my ideas into code, right? Things that you're like, oh, that'll be really easy, and then a year later you're still working on it. So that's not something that's gonna go away. You do get better at it with practice, right? This is a case where the algorithm itself is a little bit, you know, subtle, right? I walk through this a couple times, use a whiteboard to kind of draw what's happening to the references as you go. If you don't understand the algorithm, you're never going to implement it properly. Even once you understand the algorithm, it can be hard to implement it properly. Yeah, question? What's that? How do I set the reference? Well, every item has a next instance variable that's a reference to the next item. So I just change that. It's just a reference. I can set it to refer to any item. So here I would say something like, you know, whatever item 5 was, I would say item 5.next is equal to a reference to item 7. And then I would say item 7.next is equal to a reference to item 8. Yeah, good question. Other questions about this? Okay, I just want to briefly point out that what we've been talking about is something that's referred to as a singly linked list. The reason for that, sometimes just a linked list, but the reason for this is because every item has a single link to the next item. That's the minimum I have to do in order to establish order between these items. You imagine if my item didn't have a next reference, then I wouldn't have a list of items. I would just have a bunch of items, and I wouldn't know what order they were in. Okay, so at minimum, I need one link, right? I need to be able to walk the list from item to item following the next reference. But I can also add another reference to each item to the previous item, okay? This is something that's sometimes known as a doubly linked list. So in this model, every item knows not only what the next item is in the list, but it also knows what the previous item is in the list. This allows me to do a couple of nice things. The first thing it allows me to do is allows me to traverse the list in either order. So I can start at the end and move backwards. I can start at the front and move forwards. In certain cases, if I give out references to the middle of the list, this allows me to find the start or find the end, right? And so again, this is kind of what this list would end up looking like, right? Here, you'll see that my simple doubly linked list class holds 2 references. It holds a reference to the start and a reference to the end. And if I start at the end, I can walk backwards to the start. If I start at the start, I can walk forwards to the end. If I start at any item, I can walk in either direction. So I can either find the end of the list or I can find the start of the list. Now remember, we were talking a little bit about, we pointed out that with linked lists, the performance characterization of different operations on a linked list was different than an array list. That's why we had these 2 implementations, there's different trade-offs. So if I have a doubly linked list and I store a reference to the end, what does this allow me to do that might be nice? Yeah. I can add to the end of the list. How long is that gonna take, though? A 1. Remember, with the singly linked list, I could add to the beginning in 01. That was cool. That was useful. That's actually a really good feature of lists. When you guys go on, you're gonna talk, you know, you're gonna get to 225, it's gonna be like, oh, we did stacks and queues. Stacks and queues are just lists that don't have as many features, right? A queue is a list that you can't modify in the middle. You can just modify at the ends. A stack is a queue that you can only modify at one end. So I can only add or remove items from one end of a stack. So essentially, a stack and a queue are watered down versions of lists. The reason why they're useful is that by removing some of these extra features, I can actually gain a lot of performance. So imagine if your list implementation didn't have to worry about sticking things into the middle. That would mean that it would be a lot faster, right? Not only do you not have to worry about sticking things in the middle, but you can't access the middle of a queue. You can only get what's at the beginning or what's at the end. And again, there's certain algorithms for which that works great. They never need to access the interior of the list, and they get much better performance that way. But with the doubly linked list, if I store the end, now I can add things to the end in constant time, I can add things to the beginning in constant time, and if I don't allow you to access the interior of the list, if there's no get operation that takes an index, if I can only get the beginning or get the end, then all those operations are constant time, which is pretty cool. All right, so the last thing I want to point out here before we look at the runtime trade-offs between different operations on these lists is that there's, you know, I really would love to know why this happens. I don't know. It happens once, it's like once a class and never again. Okay. So this also, there's another trade-off here between the array list and the linked list. And that's a trade-off between time and space. So we're not, when we implement data structures and when we implement algorithms, we also have to think about how much memory they consume, how many, you know, bytes internally of the computer's memory is gonna be required to store the same amount of information. And you'll see here, this is my doubly linked list class. You'll see that for every item, I have to store 3 references. Every item stores 3 references, so I store a reference to the value that I'm actually storing in the linked list. I have to do that, otherwise I can't store any data in my data structure. I also hold a reference to the next item in the list and the previous item. But this means for every 1 reference that I stick into my list, remember the whole point of these data structures is to store data. So for every 1 reference of data that I stick into the list, I need 2 references of metadata, right? So essentially, I need a next and a previous reference for every piece of data I put in, right? Now again, linked lists are faster for certain operations, but they do contain more space, take up more space. An array list internally had that array. Well, the array stores exactly the right number of references for the list. So there's no wasted space in an array list. If you make the array bigger than it needs to be, then you're wasting some space. But if the array is exactly the right size, the way that you guys have been implementing, then there is no wasted space in an array list. So for every 1 reference of data, I don't need any references of metadata. I'm using the array to help me here. For linked lists, for a singly linked list, I need an extra reference. For a doubly linked list, I need 2 extra references. And so now I'm trading off space versus time. So this implementation will consume more memory to store the same amount of data, but certain operations, particularly adding and removing from the front or the back if I have a doubly linked list, are faster. Okay, so again, an array list only needs n, you know, to store n ints or n references, I only need to store n references. My linked list, you know, it's 3n for the doubly linked list. 1 for the reference, 1 for the next reference, 1 for the previous reference, 1 for the value reference. Okay, good. So now let's, you know, to say goodbye to our lists, let's finish this table. So this is really, you know, these are the interesting parts of the list interface. I've got add, and insert. So I'm distinguishing here between putting things at the front and inserting them everywhere. And actually insert, we can do insert and remove, right? Insert and remove, get and set. These are the fundamental list operations. So array list, if I stick something in the front, what was the runtime of that for the implementation that you guys finished and that we looked at in class? If I stick an item, new item into my array list, what's the runtime? Yeah. Where n is what? Yeah, it's O(n) in the size of the list. Because, remember, I mean, our chair analogy, I've gotta not only stick somebody into the chair, but I have to move everybody else in the row down 1. So that's n steps. What about a linked list? This is add to front, essentially. You guys remember what add to front looked like? Add gets worse in a linked list once you have to be able to add anywhere. But what did add to front look like? Oh, 1. Yeah, fast. So here, my linked list is the winner. It can perform insertions to the front of the list extremely fast. And removals. If I had to take an element out, remove from the front is also a 1. With an array list, if I'm gonna repack the array every time, it's ON, right? What about get and set, all right? So here, if you remember, get and set, for my array list, I just translated those directly into an array index operation, and that is constant time, right? In a linked list, what's the problem? Let's say I want to get an item that's in the middle of the list or change a reference that's in the middle of the list. I have to walk the list. In general, how many steps is that gonna take? Sometimes it'll be at the beginning, sometimes it'll be at the end, but overall, this is an ON operation. Gotta walk the list, and average ON over 2, but, you know, we're throwing out these constant factors, okay? Insert anywhere in an array list. So the general case of insert in an array list is similar to the special case of inserting it in the front. But here's an interesting caveat to all of this, which is once I need to start being able to insert items anywhere, my linked list does as badly as the array list. So it's really this special case here, adding at the front or adding at the end. I can make those constant time for my linked list implementation. And you might wonder, like, well, from this part, you know, from down here, it seems like my array list is kind of the winner, right? Because linked lists are ON for get and set, the general case, and they're ON for the general case of add or remove. Whereas my array lists at least get me a win on get and set. But it turns out that there's a lot of algorithms that only need to access the front or the end of the list. And so those algorithms do extremely well with the linked list because they don't care. They could use, you know, essentially what I was calling a queue or a stack before, a list where I can't access the interior, where I don't get these operations at all, right? So imagine I take these operations off the board, and all I can do is get and set or add and remove at the front. Now my linked list is looking a lot better. Okay, questions about this before we go on? So look, you guys now, essentially, know how lists work. If you guys went through and you read the implementation of lists in Python or JavaScript or whatever, you guys would have some sense of some of the trade-offs that would be made here. Now, let me throw some caveats out here just for fun. So, you know, our order of, you know, our big O analysis is ignoring like all sorts of interesting things that go on, okay? So the computer, the processor is this incredibly complicated beast. And it's gonna start to mess with our ON analysis in certain cases. So for example, processors are really fast at copying memory around. And so remember when we were doing those array copies, we had to move stuff? That turns out to be not as slow as we might think. So the creator of C++ actually came and gave a talk here a couple years ago. I was talking with some colleagues the other day, and apparently he pointed out that according to their tests in C++, array lists were actually faster than linked lists across the board. Just because processors are so fast at copying memory, and there's also this thing that you'll learn about in CS233 that's called memory locality, which means that when you access one piece of memory, it's fast to access other pieces that are around it. And so when I work with an array list, when I'm copying the array list, I'm always accessing chunks of memory that were initially nearby in the actual computer memory. So anyway, you guys will get a chance to think about all these cool complications and caveats in downstream courses, right? But it's fun. There's a lot of subtlety here. And to be honest, as computers continue to change and evolve, this stuff is something we have to revisit a lot, right? Because the fundamental underlying characteristics of computer processors, memory architecture, memory hierarchy, storage devices, and stuff like that all play into these decisions about how to implement these algorithms, right? That's why, we'll talk about this in a week or so, that's why there is still, you know, so you might think sorting is a solved problem. There's still an annual competition to implement efficient sorting algorithms that's held every year. And the reason is because hardware keeps changing and people keep coming up with better ways to do it. Okay, Questions about lists before we say goodbye to lists, at least in class, and sally forth? Okay. Let's talk about trees. So, the next data structure we're gonna look at in this class is something called a tree. This is not the last time you're gonna hear about trees. In fact, you may get sick of hearing about trees. Trees are an incredibly widely used data structure. They get used to store all sorts of data. They get used as a part of implementing all sorts of different types of algorithms. And so start to, get comfortable with this, right? So a tree, essentially, emulates a hierarchical data structure. To be honest, I always feel like we should probably, I started to realize this recently. I mean, we're kind of looking at our trees wrong. We always start at the top and go down, but it's sort of like you turned a tree upside down, or maybe you're looking at the roots, right? The root node is on top, and then the tree grows downward, right? I have lots of pictures. Okay, so let's introduce some terminology here so that we can have, intelligent conversations about this, all right? So in a tree consists of a set of nodes that are linked by references, but there are rules about this, right? So every parent, we can refer to a node in a tree, as a parent if it has children, so that it has nodes that are below it, right? So in this case, here's my parent node. This parent has 3 children. So the way that we're gonna construct this tree is that the parent's gonna have references to each one of its children. Its children may have references to other nodes, so they may be a parent of other nodes, okay? Now here's the important rule in a tree. This is what distinguishes it from a graph, which is a more general data structure. So in a tree, every child has one and only one parent. So if I start at any node in the tree and I walk to its parent and to its parent and to its parent, eventually I get to this node that's called the root that doesn't have a parent. This might remind you a little bit of the object hierarchy that Java uses, and that's not a bad analogy because Java does organize objects into a tree, where the root node is capital O object. So we refer to the node that's at the top of the tree, the only node in the tree that does not have a parent, as the root. A lot of our algorithms, we're gonna start on the root, and we're gonna work through the rest of the tree by moving downward. We're sort of start with the root node, then we'll examine its children, then we'll examine its children's children, et cetera, right? So here I've got a tree where I have one root node. Every tree has one root node. A single node is a tree. Not a very interesting tree, but a single node is still a tree. Just like a single item is still a list. Here, my root node has one child. That node has 2 children, and then this node has 1 children. This is an example of a tree. So children that don't have any leaves, so if my tree has a finite number of elements, which the trees that we work with will, if I start at the top and I work my way downward, eventually I'm gonna get to a place where I find nodes that don't have any children. We refer to those nodes as leaves. This is where the tree stops growing, right? So, a tree can have an arbitrary number of leaves, right? It certainly can't have more leaves than it has nodes. Depends on the structure of the tree. But again, with a finite-sized tree, if I start at the top and work my way downward, eventually I'm gonna find myself at leaf nodes, right? So this node's not a leaf because it has children, this node's not a leaf because it has one child, this node's not a leaf because it has one child, this node and this node have no children. Therefore they are leaves. All right. So we can talk about the level that a node is at in the tree. And we enumerate this, sometimes referred to as depth. We enumerate this by starting with the root. The depth of a node in the tree is the number of steps it takes me starting at the root to get to that node. So here I've got, again, a tree. I've highlighted the root node that's at level or depth 0. It has 2 children. Because it took 1 step to get to those children, they're at depth 1. One of those children has another child, so now it's taking me 2 steps to get to that child. So depth 2. And then this leaf node down here is at depth 3. So the height of the height of a tree is the maximum number of steps it takes to get from the root to any leaf node. So the height of this tree is 3, okay? It's not 1 because there's a deeper branch over here that I need to go down. Okay. Any questions about this terminology before we go on? You know, and again, I think, you know, if you think about just sort of, you know, turning these things upside down, the tree growing upwards, or these kind of being like roots descending, it doesn't matter, right? The tree grows downward, right? The trees that you see out there that are nice and pretty, particularly this time of year, they grow upward. All right, any questions about this? Yeah. Yeah, so the question is like, what's the difference between a tree and a linked list? So in a linked list, every item had one next item. In a tree, every node can have one or more children. So it's a great point. If I eliminate this node here, what I have here is a linked list. But the fact that this node has 2 children makes this a tree, okay? In general, trees can have, in a tree, a node can have as many children as it wants. A lot of the trees that we look at in this class are gonna be what are called binary trees, where every node has either 1 or 2 children. 0, 1, or 2 children, but not 3 or 4 or 5. Right, but again, you can create trees, and they're useful, and you guys will work with them when you get to 225, that have where every, node has an arbitrary number of children. It's a good question, though. So this is, in some level, a generalization of a list. We usually don't think of it that way, but that's kind of what it is. Good question. Other questions about trees before we go on and talk a little bit about why? Okay, so let me try to motivate all of this work because we're gonna have a lot of fun with trees over the next couple weeks, particularly writing recursive algorithms to run on those trees, right? Which is gonna, you know, recursion is one of those concepts that is going to hurt your brain the first time you learn it. It's gonna give you a mental workout. It is not easy to think about. It's not easy to get to work. We're gonna give you a lot of practice, but I'm just warning you. Like I remember years ago taking my second semester programming class and encountering recursion and being like, you know, and it just took me a long time to wrap my head around what was happening. And trees are going to be our friend here that we're gonna work with. So what can we do with these things? Why do we use trees at all? What kind of data can we store in them? So like I hinted at before, the Java class hierarchy represents a tree. Why? Every node, every object in Java has a parent, one parent, okay? If I don't extend something explicitly, I get capital object. If I do, I get whatever I extended. But that determines where that node, where that class attaches to the tree, okay? You know, and the fact that I can only extend one class means that this becomes a tree. If I could extend multiple classes, it would be more complicated. It would not be a tree. But every node has one parent, except for one node. So the root of the Java class hierarchy is capital O object. It has no parent, but it's the only object in Java's type system that does not, it's the only class in Java's type system that does not have a parent, okay? So there are, you know, again, you guys are only sort of like subliminally aware of this, I think, but there is data on your computer. Right? People aware of this? Like your computer stores data? Like there's data that's there, like if you turn it off and turn it back on, it's still there. And I'm not teasing you about this. I've been talking with some of my colleagues, and the fact is that like, the world is so different now than when we grew up, you know, I can certainly forgive you for thinking that all of your stuff lives in the cloud, which is not actually that bad of a model, right? You can actually kind of operate that way today. But it turns out that there's actually data on your computer. That data is stored in chunks that are referred to as files. Every one of those files has a name, and they're organized hierarchically. And the way that they're organized, particularly on Linux or Unix-like systems like Macs, and you know, if you have a laptop that runs Linux, is into a tree, where they say single root, and then the names of the files on your computer all descend from that, right? So that's another place where we see trees. Internet domain names, all right? So this is sort of interesting. Here's another place where we have a tree, okay? So what's the, so first of all, what's a domain name? Give me an example of a domain name on the internet. You guys use these all the time. You probably don't know what they are, or maybe you do. Give me an example of one, yeah. Oh, well, so those are what are called top-level domains, but just give me a full domain name. You're on the right track. Give me a full domain name. Give me an example of one. How about www.google.com? It's a domain name. You type it into your browser, you end up at a website, right? The dots in that separate different parts of the domain name for the purposes of organizing the way that we control domain names into a tree, right? So, you know, the person who answered the question pointed out .com, .edu, .org. These are what are called top-level domains. That's the first level of the tree. Those names are at level 1. The next level for www.google.com would be .google. The next level is www. The reason why we organize these names into a tree is because this also represents who controls the name. So there's an organization that controls the .coms and the .edus and the .funds and all the new ones that they just created, right? So at some point, Google had to go to them and apply to get access to .google.com. But everything after that, docs.google.com, music.google.com, I know this is sounding like a Google ad, right? But whatever, replace Google with Apple or Facebook or whatever you want. All of the names below that are controlled by Google. Google doesn't have to talk to anybody. If Google wants to put up aprilfools.google.com, Google gets to make that choice because that's controlled by Google now, right? And you can actually create more levels of that. So cs125.cs.illinois.edu. .edu is controlled by this organization. At some point, Illinois applied and they got access to use .illinois for the University of Illinois. Even on campus though, so cs.cs, those domain names are controlled by the CS department. So if I want one of them, which I did like 2 years ago, I just go down the hall and I talk to someone who works in the building and I say, hey, can I get cs125.cs.illinois.edu? And they were like, yeah, sure, right? So this, you know, the structure here represents how the domain names are managed. And, you know, we find a lot of data in the world that has this sort of hierarchical structure, right? Because the hierarchical structure in Java allows me to inherit and determine what a class does, what properties it has. You know, for your computer, it allows you to name files and to organize them into folders and stuff like that. And for internet domain names, it represents the control, right? So as you go from the .edu to .illinois to .cs, you're going from, you know, a group of people that I've never met who control who gets access to .edu to a group of people that I know on a first-name basis who control .cs, right? All right, so, and again, it is just some extra pictures. So here's the, you know, example of the Java class hierarchy. Here's what it looks like. It's a tree, right? Here's files on your computer. Yeah. At some point when you guys get into 225 or 126, you guys will maybe start poking around using a interface to your computer called the command line that allows you to look at all of the files on your computer. And they're actually, this isn't all the files on my computer, but this is a snapshot of them. They're organized in this way. They end up organized into a tree. And then again, like I said, domain name, the way that domain names are translated, right? So both cs125.form and .cs are both domain names that I got by talking to somebody who works in the CS department who controls all of this space. So if you want to put something in front of .cs, you know who to talk to. The only thing that's a little confusing about domain names, and actually some of the people that designed this system said they always regretted that they're backwards, right? So you could have typed com.google.www, and that would have been also okay, right? That makes a little more sense. It's like top down, right? But they're all reversed, right? So the more general part is at the end, the lower part, the leaf, is at the front, the root is at the end. All right. So the data structure we're gonna work with in this class is known as a binary tree. So a binary tree is a special case of a tree where each node has 1 or 2 children, or 0. 0, 1, or 2 children. At most, 2 children. Here's how we are going to represent our tree data structure. And this is kind of cool, actually, right? So this is my tree class, and it consists of 3 references, 3 instance variables. Every node in the tree, we want to be able to store data in it. A lot of times when we work with trees in this class, we're gonna be concerned primarily with examining their structure. But trees store data. Again, you know, for example, the tree that stores all the different domain names on the internet is used all the time, every time you go to an address in your browser. And so we need to store information about, you know, the domain names that the tree represents. So just like my linked list item class, I have a value, I have a reference to a value, and then I have 2 references here. Now I could have like a list of references or an array of references, but with the binary tree, the nice thing is I know that I'm only gonna have 0, 1, or 2, and it's also helpful to name them, right? So I'm gonna name them right and left. So every node's gonna have either a right child, or a left child, or both, or neither. I represent not having a child by this reference being null. So if my right child is null, I don't have a right child. If my left child is null, I don't have a left child. If both are null, then I'm a leaf node. I don't have any children. All right, so this is what we're going to work with. And when we look at these graphically, we'll also, that's where the right and left comes in handy as well, because that'll refer to which side of the parent that node is hanging off of, right? If it's a right child, it hangs off on the right, left, left. Okay, so now here's where we get to make this cool connection with recursion as an algorithmic technique. So let's just start with an observation here. If I look at this tree, and this is also true of lists, but I wanna point it out with trees. Every subtree of this tree, if I break off a part of this tree, it's a tree, okay? So no matter how I break this tree into smaller pieces, the pieces that I end up with are themselves trees. So here's an example. Let's say I just look at the left subtree of the root. So the root here is the node with value 1. Its left subtree is the subtree that starts with the node with value 3. Okay? It has a single child, and then its child has a couple of childs. But this, if you just like squint a little bit and only look at the blue nodes, that's a tree. It has a different root. Rather than root 1, I have an object with root 3, value 3. Instead of having, let's see, 3, 6, 9 nodes, I have 4 nodes, but it's still a tree, okay? If I look at 3's subtree, so if I look at the subtrees of 3, there's only 1, because 3 only has 1 child. This is also a tree. Again, it's a smaller tree. Here's the other thing that's cool about this. The trees are getting smaller. This is gonna be really helpful for us when we start to write our recursive algorithms. So I went from having a tree with 9 nodes, now I'm looking at a tree rooted at node 4 that has 3 nodes. And I can keep doing this. A single node is a tree. So now I've reduced the problem to a tree that has 1 node. Like a tree with 1 node, 8 is also a tree with 1 node. Now I can start down the other side and do the exactly same thing. So the tree that's the subtree of the tree rooted at node 1 that's rooted at node 5 is itself a tree. I could consider it completely separately. It's a tree with 4 nodes. And then the tree rooted at 7 is a tree, here's another tree. So as I descend into this tree, what I did was I started out with a problem where, you know, I had 9 nodes that I needed to think about, a 9-node tree. And I reduced it to a series of problems where I was only thinking about 1 tree, a 1-node tree. And you can see this in the definition of our tree class. So recursion, the actual definition of recursion, you guys are gonna start to think I don't want you to think narrowly about recursion. Recursion is a very broad set of ideas and problem-solving techniques. Recursion is not when a function calls itself. That's an implementation, one possible implementation of a recursive algorithm. You know, recursion is not even an algorithm. Recursion also can be used to describe a data structure. So recursion occurs when something is defined in terms of itself. Look at my tree class. My tree class And again, the same thing was true for lists. We just didn't stop to point it out. My tree class says that a tree consists of one value and then references to two other trees. Right? So this is a recursive data structure. In order to define it, I have to continue to try to define it, right? So it's defined in terms of itself. I have references to myself here as part of the definition, right? And that's why this is true, right? Because if you think about it, if I go all the way up to my first node, node 1 is gonna be if I represented this in Java using this class, node 1 is going to be a tree where the object, the value is gonna refer to an object like the integer 1, but then it has a tree, a reference to a tree that's its left subtree and a reference to a tree that is right subtree. So this sort of, hopefully these two things connected together make it very clear how this recursive definition works. So again, you know, recursion as an algorithmic technique is a way of decomposing a problem so that what we do is we take a big problem and we break it down into smaller pieces. The solution to the big problem depends on the solution to the smaller pieces. But we keep doing this until we find problems that are really small, where the solution doesn't depend on smaller pieces. And then we reconstruct a solution to the larger problem. That probably made very little sense. So let's see some examples about how to do this. But so far, let me distinguish between what we've done before. So one of the things we've done before, the ways that we've approached problems, sometimes are referred to as iterative, okay? We have looked at iterative solutions throughout this class. What you guys did, what you're doing with the linked list right now, when you're walking through it, that's an iterative approach to walking a list. There's also a recursive way to get to every item in a list. I don't teach that because I don't think it's very useful. I think the better way to go through a list is to use an iterative loop. It's also a great chance to practice with references. Trees, on the other hand, are a great fit for recursion, okay? So with iteration, what I'm doing is repeating the same steps over and over again until I'm done. With a recursive solution, I'm breaking the problem into smaller and smaller pieces until I find one that is small enough that I can solve it easily. Okay, so let's talk about counting. One of the most basic things that I probably want to be able to do with the tree is to determine how many nodes does the tree have. I wanna count the number of nodes in the tree. All right, so if I was approaching this problem iteratively, what I would need to do is I would have to find a way to visit every node in the tree. So let's say I give you a reference to node 5, which is the root, the node with value 5. And then if I can write a loop that goes through all the nodes in this tree one by one, then what I can do is I can just keep a counter inside my loop and I just increment it every time, and I'm done. When you guys implement size for linked lists, this is how you're gonna do it, right? And so I can do this. I could basically, you know, now here's the trick with trees though. Here's what I wanna warn you about. At some point, maybe in a few classes once we've had some practice with recursion, try to write this loop, okay? It is not easy. It's not impossible. You have to use some other data structures and stuff like that. It can be done. But it is not natural. It's not gonna be as nice as you think. It certainly is not gonna look as nice as that linked list for loop that we wrote. That one's nice. The reason is every item in a linked list only has one item after it. Here, I've got cases where I've got two items. So how do I handle that? Yeah. Like I said, at some point we'll come back, or I'll leave this as an exercise to the listener to come back and try that. So how would we approach this problem recursively? Okay, so the trick with a recursive algorithm is to make the problem smaller. And then do that until I have a problem that's so small that it's so easy to solve. And then try to figure out how to combine the results from my problems. All right, so here's how I'm gonna approach this for counting. We'll come back and we'll implement this on Friday together. So I wanna break the problem down into smaller pieces. So how do I do that? Okay? So this is in general, this is our pattern for recursive algorithms. Break the problem into smaller pieces, continue that until I find a really small problem that I can't avoid solving, and then combine the results together in a way that's appropriate to the problem I'm trying to solve. All right, so here's what I'm gonna do. You gave me a tree. You gave me a reference to a tree rooted at node 5. I know I can make this problem smaller, and here's how. I'm gonna consider the left subtree of 5 and the right subtree of 5 to be smaller problems. So essentially I'm gonna say, look, I don't know how to count the whole tree, but here's what I know. If I could count the left subtree, and if I could count the right subtree, and if I knew how many nodes were in the left subtree and knew how many nodes were in the right subtree, I would know how many nodes are in the tree, right? Because it would be left plus right plus 1 for me, okay? So essentially I'm saying, I don't know how to solve the problem. But I do know that if I could solve the problem of counting my left subtree and solve the problem of counting my right subtree, then I would be able to solve the problem, okay? So now, here's what we do. We just start over on the left subtree. We pretend that it's the only subtree in the world. So now I say, oh, you know what? If I could only count my left subtree, I don't even have a right subtree. If I could count my left subtree, I would know how many nodes are in this tree, because it would be the number of my left subtree plus me, plus 1. My right subtree is empty. So now I start I start the algorithm over again, and now I pretend that the only tree in the world is the tree that's rooted at node 7, okay? Now what do I need to do? So I made the problem smaller, I made the problem smaller. Now I'm in a problem that is so small that I have to solve it. This node has no children. How many nodes are in the tree rooted at node 7? 1. I know that. I know the answer, right? So I finally found a problem that's so small that I know how to answer it, okay? But remember, I'm gonna keep doing this in my other subtrees. So I'm gonna say, okay, if I could figure out how to count the left subtree of 10 and the right subtree of 10, then I would know how many nodes are in the tree rooted at 10, because it would be left subtree plus right subtree plus 1. And again, now I'm in a leaf node. So now I know how many nodes are in this tree. Now I go over to node 1, I'm again in a leaf node, I know how many nodes are in this tree. So now what I start to do is combine the results. So remember, 3 said, hey, if I could count my left subtree, I would be done, because I would know how many nodes are in that tree. And 10 said, hey, if I could count my left subtree and my right subtree, I would also be done, because I would add myself. So now what I'm starting to do is integrate the results back together, bring the problem back together. I broke it down until it was really easy, and now I'm combining the results. So now I know how many nodes are in the left subtree of node 5. And I also know how many nodes are in the right subtree of node 5. And again, where I started at the very beginning is node 5 said, if you can count the nodes in my left subtree and the nodes in my right subtree, I know how many nodes are in the tree. And at this point, I do. All right, we'll pick up here on Friday, and we'll write some code to solve this problem. I do not have office hours today. I had them on Monday. Good luck on the midterm if you're taking it today. I know many of you are. I will see you guys on Friday. Stay dry.